Calculating limits using the limit laws. Let's take a look at the basic limit laws. These are all very intuitive. Let's go through them. The first limit says if you take the limit of the sum of two functions, this is equal to the sum of the limit of the two functions, assuming that the original limits of the independent functions exist. The same can be said for the limit of the difference between two functions, the limit of a constant multiple of a function is the constant multiple times the limit of the function. The limit of the product of two functions is the product of the limits. And finally, the limit of the quotient of two functions is the quotient of the limits as long as the limit of the bottom function is not 0. In the first example, the graphs of f and g are given below. We're going to use them to evaluate each of the following limits. So to evaluate all of these limits, the first thing we need to know is what is the limit of f of x and g of x as x approaches the various numbers that we see here. So let's start with part A here. What is the limit as x approaches 2 of f of x? Well, if we look at the graph of f of x, which is this graph right here, we can see that x equals 2 is here, and as we approach 2, the function values are getting closer to this value here, which is at y equals -1. So the limit of f of x as x approaches 2 is -1. The limit of g of x as x approaches 2 can also be found in the same manner. And so here is the graph of g of x, and here is x equals 2. And we can see as we approach 2, the values of the function are approaching this value, which is y equals 2. So the limit as x approaches 2 of g of x is 2. So now in part A, they want us to find the limit as x approaches 2 of f of x plus g of x. And we know that if the independent limits exist, this is going to be the same as the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. And we know what these are because we just calculated them. So the limit of f of x as x approaches 2 is -1 plus the limit of g of x as x approaches 2 is 2, and -1 plus 2 is +1. Now let's do the same for part B. In part B, we have the limit as x approaches 0 of f of x minus g of x. So as long as the independent limits exist, this will be equal to the limit as x approaches 0 of f of x minus the limit as x approaches 0 of g of x. Now, what is the limit as x approaches 0 of f of x? Let's look at the graph. So here is the graph of f of x. As x is approaching 0, we can see the values of the function are approaching 2. And for g of x, as x approaches 0, like this, you can see that the limit here does not exist, because if we take the limit from the right side, we get 1. But if we take the limit from the left side of 0, we get 3. So this limit does not exist. So even though the limit as x approaches 0 of f of x is 2, this limit right here does not exist. And if that's the case, then the whole limit does not exist. For part C, we want to find the limit as x approaches -1 of f of x times g of x. Again, using the limit laws, we know that this should be equal to the limit as x approaches -1 of f of x multiplied by the limit as x approaches -1 of g of x. Now let's look at the graphs. As x approaches -1, which is right here, the values on f are getting closer to this number, which is y equals 1. So the limit of f of x as x approaches -1 is 1. And we're going to multiply that by the limit of g of x as x approaches -1. And again, -1 is here. As x approaches -1, the values of g of x are approaching this number here, which is y equals 2. So both limits exist, and now we just multiply those results together. 1 times 2 is 2. For part D, the limit as x approaches 3 of f of x divided by g of x will be equal to the limit as x approaches 3 of f of x divided by the limit as x approaches 3 of g of x, as long as these limits exist and as long as the limit of g of x is not 0. So let's go ahead and find these limits. So as x approaches 3, which is right here, the values of f of x are clearly getting close to this number, which is 1, divided by, and the limit as x approaches 3 of g of x, so here is x equals 3, and the values of g as x approaches 3 are 0. Okay, so we have a problem, right? Because we cannot divide by 0. So in this case, we actually can't use this limit law, because since the limit in the denominator is 0, the overall limit here, we have to say, does not exist. To do part E, we actually need a few more limit laws. So let's take a look at the rest of the laws. The sixth law says that if you take the limit of f of x to the n power, it's the same as the limit of f of x, quantity to the n power. The same thing is true for the nth root. So if you have the limit of a radical, you can take the radical of the limit. Limit of a constant is a constant. The limit of x as x approaches a is just a. Limit of x to the n as x approaches a is a to the n. And finally, the limit of the nth root of x as x approaches a is the nth root of a. So going back to our example here, if I want to take the limit of x squared times f of x, I know this is equal to the limit as x approaches 2 of x squared multiplied by the limit as x approaches 2 of f of x. Now, how do we do the limit as x approaches 2 of x squared? Well, again, this rule right here tells us that if we have the limit of x to the n, all we have to do is plug the number a in for x. So the limit as x approaches 2 of x squared is just going to be 2 squared. And we're going to multiply that by the limit as x approaches 2 of f of x. Looking at the graph of f of x, here is x equals 2. Clearly, as x approaches 2, the values of the function are approaching -1. So this is -1, and we have 4 multiplied by -1, which is -4. And finally, part F, we have the expression f of -1 plus the limit as x approaches -1 of g of x. So to evaluate this expression, first let's just calculate what is f of -1. So on the graph of f, here is -1, and f of -1 is this point up here, right? So it's not the same as the limit, it's the actual function value at -1. So we know that that value is 3 plus, and then we have the limit of g of x as x approaches -1. Again, -1 is right here. As x approaches -1, the values of g are clearly getting closer to y equals 2. And so we have 3 plus 2, which is equal to 5. We've already discussed these additional limit laws, so let's go ahead and take a look at a second example here. Part A says find the limit as x approaches 5 of the function 2x squared minus 3x plus 4. So the limit laws here tell us that we can take the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x, and then plus the limit as x approaches 5 of the number 4. The next law that I can apply is the constant multiple of the variable here can be factored out of the limit. That is this property right here. Actually, it's on the previous page. There we go. Oh, here we go. Sorry about that. So we have the limit as x approaches a of c times f of x is c times the limit as x approaches a of f of x. So what that means, my apologies here, what that means is that we can factor out the 2 here. So we get 2 times the limit as x approaches 5 of x squared minus, here we can pull out the 3 times the limit as x approaches 5 of x, and then plus the limit as x approaches 5 of the number 4. Now, to evaluate the limit of x squared, we know that all we have to do here is plug 5 into there. So this is going to become 2 times 5 squared minus 3 times the limit as x approaches 5 of x. Again, we just plug 5 in for x, which just gives us 5. And then plus the limit of a constant is a constant. And if you do the math here, we have 2 times 25, which is 50, minus 3 times 5, which is 15, plus 4, and this is 35 plus 4, which is 39. For part B, it's very similar. To evaluate the limit here, first we are going to apply the rule that says the limit of a quotient of two functions is going to be the limit of the top function divided by the limit of the bottom function, as long as that bottom function does not become 0 when you take the limit. The limit of the top we can now break apart, so we have the limit as x approaches negative 2 of x cubed plus, and then now I'm going to take the limit of the second term, and simultaneously I'm going to factor out the 2, so we get 2 times the limit as x approaches negative 2 of x squared, and then minus the limit as x approaches negative 2 of 1. In the denominator, I have the limit as x approaches negative 2 of 5, minus 3 times the limit as x approaches negative 2 of x. And now to evaluate these limits, we can use the rule that says you can simply substitute negative 2 in for x. And so doing that here, we get negative 2 to the third power plus 2 times negative 2 to the second power minus the limit of a constant is a constant. In the denominator, the limit of a constant is a constant. And then minus 3 times substitute negative 2 for x. And now just do the math. We have negative 8 plus 2 times 4 is positive 8 minus 1 divided by 5 plus 6, and this is going to be negative 1 over 11. Let's take a look at the direct substitution property. This states that if the function f is a polynomial or a rational function, and a is a number in the domain of f, then the limit of f of x is simply f of a. So what this means is that if I have, for example, the limit as x approaches 3 of x squared plus 5x, I no longer have to use all the limit laws to do this limit. X squared plus 5x is a polynomial, and I can plug the number 3 into this polynomial to get the answer here. And so this answer would simply be 24. Likewise, if I have the limit as x approaches 2 of x squared divided by x squared minus 1, which would be a rational function, as long as plugging in this number doesn't make the denominator 0, I can just plug in the number to evaluate the limit. And so this would be equal to 2 squared divided by 2 squared minus 1, which would be 4 over 3. This is going to be very helpful in evaluating limits in the upcoming examples. In the next example, you have to be a little bit more careful. If you take this limit by applying the limit to the numerator and denominator, you will find out after using all the limit laws that you will get 0 divided by 0. And this is a problem. Anytime you get 0 divided by 0, it means that you must algebraically simplify your original function. So what do I mean by this? Well, let's think about what we can do to this function. So we have our limit. In the numerator, we have x squared plus 3x, and in the denominator, x squared minus x minus 12. We can simplify this expression by factoring the numerator and factoring the denominator. So x squared plus 3x will factor into x times x plus 3, and x squared minus x minus 12 will factor into x minus 4 times x plus 3. Then I want you to notice that we now have a common factor of x plus 3 that we can cancel out. And this becomes the limit as x approaches negative 3 of x over x minus 4. And now if we take the limit of the numerator divided by the limit of the denominator, we can apply the limit laws and get an answer of negative 3 divided by negative 7, which is 3/7. So anytime your original limit ends up being 0 divided by 0, you must look to simplify the original expression. In the next example, this is very similar. If you apply the limit laws here, you will end up getting 0 divided by 0. You can pause this video and verify that for yourself. So again, it means that we must algebraically simplify the original function. And so the function that we have here is the square root of t squared plus 9 minus 3 all divided by t squared. So the question is, how do you simplify this? It's not as easy as the last problem. So when you have an expression involving radicals, there is a trick for simplifying these called multiplying by the conjugate. So I'm going to multiply by the square root of t squared plus 9 plus 3. And whatever I do to the numerator, I must do the same thing to the denominator. So this is called the conjugate because this negative sign here is changed to a positive sign when we multiply by this conjugate. Now, why is this the way to do it? Well, what you have to do is go through and do the multiplication to see what happens next. So when we multiply these together, let's go ahead and put down our limit. We are going to have the square root of t squared plus 9 multiplied by the square root of t squared plus 9. And that is going to be t squared plus 9. Then we have the square root of t squared plus 9 times positive 3, which is positive 3 times the square root of t squared plus 9. Next, we have negative 3 times the square root of t squared plus 9, which is going to be negative 3 square root of t squared plus 9. And finally, negative 3 times positive 3 is negative 9. Now, we'll pause here for a second, go ahead and go to the denominator. The trick in the denominator is don't multiply this out. Only multiply the conjugates. So in the denominator, I'm going to keep t squared factored out multiplied by t squared plus 9 plus 3. Okay, so don't distribute there. What you should notice is that in the numerator, these terms cancel out, and also 9 minus 9 cancels out. And so we get a greatly simplified expression in the numerator. We have t squared, and in the denominator, we have t squared multiplied by the square root of t squared plus 9 plus 3. And here's where the magic occurs. This t squared and this t squared cancel out, leaving us with a 1 in the numerator. And now this is simply the limit as t approaches 0 of 1 divided by the square root of t squared plus 9 plus 3. I can now use the limit laws by taking the limit of the top divided by the limit of the bottom. And then I will apply this limit to each one of these, which gives us this. And then when you have a limit of a radical, you can put the limit inside of the radical. That is one of our properties. And that will make it look like this. And now the limit of 1 is 1. The limit of 3 is 3. And right here, to take this limit, you can plug in 0 for t, and that is going to give you the square root of 9. And this becomes 1 divided by 3 plus 3, which is 1/6. In the next example, this is yet another example of getting 0 divided by 0. So if you take the limit as h approaches 0, clearly the denominator becomes 0. And as h approaches 0 on top, you get 3 squared, which is 9, minus 9 is 0. So again, anytime you get 0 divided by 0, what you need to do is try to simplify the expression. Now, in this case, we can multiply this out. So let's remember that 3 plus h to the second power means 3 plus h multiplied by 3 plus h. And if you multiply this out, you will get 9 plus 6h plus h squared. And I'll go ahead and fill that in down here. And then we have minus 9, and then all divided by h. And this one doesn't require any tricks. 9 minus 9 cancels out, and so this becomes the limit as h approaches 0 of 6h plus h squared divided by h. Now, if you just plug in 0, you're still going to get 0 divided by 0. So notice on top, you can factor out a common factor of h, leaving us with 6 plus h left over. And then now the h's cancel out. And this just becomes the limit as h approaches 0 of 6 plus h. And this becomes 6 plus 0, which is 6. In the next example, once again, if we allow h to be 0, the numerator will become 1 over x squared minus 1 over x squared, which is 0, and the denominator will also be 0. So yet again, we get 0 divided by 0, which means yet again, we need to simplify this expression. So this is perhaps the most complicated. How do you simplify an expression like this where you have smaller fractions inside of a larger fraction? This is called a complex fraction. And the way you simplify a complex fraction, or I should say one way you can simplify a complex fraction, is identify the least common denominator of your fractions here. And that least common denominator is going to be x squared times x plus h squared. And then what I'm going to do is take this numerator and multiply it by x squared times x plus h squared. And I'm also going to multiply the denominator by x squared and x plus h squared. Now, what this does in the numerator, when you distribute this to each of these, it's going to give you a pretty big expression. Let's go ahead and take a look at that. So distributing this to each of these terms gives you this expression. Sometimes you might find it helpful to go ahead and put a 1 underneath these. And the idea here is that when you multiply two fractions like this, you can cross-cancel any like factors. So x plus h quantity squared will cancel with this, and over here x squared will cancel with x squared. And so in the numerator, what you have here is the limit as h goes to 0. All that's left out of all of this is x squared, minus all that is left here is x plus h quantity squared. And in the denominator, we have h times x squared times x plus h squared. So again, in the denominator, all you're doing is multiplying the h by your common denominator here, but don't multiply any of this out. Leave this in factored form. Now what we can do is we can go ahead and multiply out x plus h to the second power. So let's remind ourselves that if we FOIL this, we will find that x plus h squared is x squared plus 2xh plus h squared. So this becomes x squared minus, and again, this is going to be replaced with this. But when you replace it, you need to use parentheses. And the reason you need to use parentheses is because that negative is going to get distributed to all three of these. And so this becomes the limit as h goes to 0. We have x squared minus 2xh minus h squared, all divided by the same denominator. Now the x squared minus x squared cancels out. And what I have left is the limit of negative 2xh minus h squared divided by same thing. Okay, now if you let h equal 0, you will still get 0 divided by 0 here. So what we are looking to do in the numerator is factor out an h so that we can cancel it with the h in the denominator. So in that numerator, if I pull out an h, what I have left is negative 2x minus h, and then the denominator. And now see the h cancels out with the h. And we end up with the limit as h goes to 0, negative 2x minus h divided by x squared times x plus h squared. And now essentially to complete this limit, all you have to do is let h equal 0. Okay? So if you plug h equals 0 in here and in here, you will get negative 2x minus 0 divided by x squared times x plus 0 squared. And this is negative 2x divided by x squared times x squared, which is negative 2x divided by x to the fourth. And finally, you can cancel the x in the numerator with one of these x's, which will leave you with 3 in the denominator. And so our final answer here is negative 2 over x to the third power. And again, I know this can seem really complicated and, maybe even a little bit intimidating, but with practice, you too will get good at simplifying these expressions. Next, we have a theorem. The theorem says that the limit as x approaches a of a function is equal to L if and only if the limit as x approaches a from the left is equal to L and the limit as x approaches a from the right of f is equal to L. So that is to say, the limit as x approaches a will only equal L if both the left and right limits as you approach a also equal L. So in this example, we want to find whether the limit as x approaches 4 of f of x exists. And we have a piecewise defined function here. So at first, I'm just going to write down limit as x approaches 4 of f of x is equal to what? Well, f of x is defined to be two different functions depending on what the value of x is. If x is larger than 4, f of x is this function. And if x is less than 4, f of x is this function. Okay? And sometimes it's helpful to put that on a number line. So here is the number 4. For all x's that are greater than 4, f of x is going to be the square root of x minus 4. And if x is less than 4, f of x is going to be 8 minus 2x. So to determine whether the limit as x approaches 4 of f of x exists, I have to take the limit as x approaches 4 from the left of f of x, and I have to take the limit as x approaches 4 from the right of f of x. So let's first talk about the limit as x approaches 4 from the left. If I'm approaching 4 from the left, we are approaching 4 here. And that means that we are talking about this function. So this limit becomes the limit as x approaches 4 from the left, and f of x in this case is 8 minus 2x. And to evaluate this limit, all we have to do is plug in x equals 4, and this gives us 8 minus 8, which is 0. The limit as we approach 4 from the right, so if we're approaching 4 from the right, we are over here, which means we are looking at this function. So as we approach 4 from the right, we can rewrite this limit x approaches 4 from the right of the square root of x minus 4. The limit laws allow us to bring the limit inside the square root. And finally, we can evaluate this by simply plugging 4 in for x, and this gives us the square root of 0, which is equal to 0. Now, since the limit as we approach 4 from the left is 0, and the limit as we approach 4 from the right is also 0, we now know the limit as x approaches 4 from both sides is also equal to 0 because of this theorem. Our next example is actually very similar, even though it may not appear to be at first. If you try to do this limit by substituting in x equals negative 2, you will find that this limit will once again be 0 divided by 0. So how are we going to do this limit? Well, what we need to do is remember what it means to be the absolute value of x. So let's talk about the definition of the absolute value of x. So the absolute value of x is x if x is greater than or equal to 0. And the absolute value of x is the opposite of x if x is less than 0. So the absolute value function is a piecewise defined function. So if I'm taking the limit as x approaches negative 2, negative 2 is a number that is less than 0. So for this particular limit, the absolute value of x is going to be negative x, right? Because negative 2 is a number that is less than 0. So what we can do is we can take this limit and we can say the absolute value of x can be replaced with negative x. So I'm going to replace the absolute value of x here with negative x. And if I do that, I get this expression. But this is the limit as x approaches negative 2 of 2 plus x divided by 2 plus x. Now again, if you just plug in negative 2 right now, you're still going to get 0 divided by 0. But we know 2 plus x divided by 2 plus x cancels out. And so this literally becomes the limit as x approaches -2 of 1, because 2 plus x divided by 2 plus x is 1. And so this overall limit is 1, because the limit of a constant is a constant. So the absolute value function is always a piecewise defined function when you write that absolute value without using absolute values. So you need to really get used to the definition of an absolute value, because it's going to come up in multiple different applications. Okay, next we take a look at a couple of theorems. The first theorem says if f of x is less than g of x near a, then the limit as x approaches a of f of x must be less than the limit as x approaches a of g of x. That is a pretty intuitive theorem. And the next theorem just takes it to a little higher level. It says if g of x is smaller than h of x, but bigger than f of x near a, and if the limit of f of x and the limit of h of x both equal L, then the limit of g of x must also equal L. And there's a good diagram down below to help us understand what's happening here. So I want you to notice that the function g is in between the function h and the function f. That is, g is smaller than h, right, because it is below h, but it is bigger than f, because it is above f. If the limit of the bottom function and the limit of the top function both approach the same value, L, then the limit of the middle function gets squeezed in between those two and must approach that same limit. And this is what we call the squeeze theorem. Let's take a look at an example. Here we want to show that the limit as x approaches 0 of x squared times the sine of 1 over x is equal to 0. And I need to point out in the beginning that if you just take the limit as x approaches 0 of sine of 1 over x, this limit does not exist, right? Because if you plug in 0, 1 divided by 0 does not exist, and the sine of something that does not exist also does not exist. So what we have to do here is just recognize from trigonometry that sine of an angle theta is always in between 1 and -1. This is always true for sine. It's also true for cosine. So what it means in this particular case is the sine of 1 divided by x must be a number in between -1 and +1. Okay, this must be true. Now, if I take this inequality and I multiply the left side by x squared, and I multiply the right side by x squared, and I also have to multiply the middle by x squared, then what we get is -x squared is less than or equal to x squared times the sine of 1 over x is less than or equal to +x squared. So what you can see here, I hope, is that from the squeeze theorem, this is our f of x, this is our h of x, and in the middle we have our g of x. But what is the limit as x approaches 0 of -x squared? Well, we know that it's 0. And what is the limit as x approaches 0 of +x squared? This is also 0. So this function is going to 0 as x approaches 0, and this function is going to 0 as x approaches 0. Therefore, by the squeeze theorem, this means the limit as x approaches 0 of x squared times the sine of 1 over x must also be going to 0. Okay, and this must be true by the squeeze theorem. And this concludes this section.